Hello and welcome to Physics Teacher. In this video, I'm going to be going over a lab that I do with my grade 12 chemistry students where we will be determining the molar heat of combustion for ethanol. I do have a lab handout if you would like. It is available for free in the description, so go grab that and then we'll start the lab. All right, first let's go over what equipment we have. So here we have a retort stand, the ring clamp. We have a clay triangle, and underneath we have an evaporating dish. Okay, we have a digital thermometer. This is made out of aluminum, so that's important because we need to know the specific heat capacity for aluminum. I have some ethanol, matches, and of course we need a digital scale and some graduated cylinders. So let's get the masses of some of these objects first. So I'll zero this, and let's start with the aluminum can. The aluminum can is 60.190 or 197 grams. Okay. Now we're going to get the mass of water. Now I'm going to use about 100 milliliters. I'm just saying about, we're not going to use the density of water to calculate it. Instead, we're going to determine the mass of the cylinder and then the mass of the cylinder with the water. And you can subtract those two. So the graduated cylinder on its own is 46.810 grams. Now let's get some water. Okay, here we have about 100 milliliters of water. So together we have a mass of 144.7056 grams. So you can subtract those two to figure out the mass of the water. Now we have ethanol. On the handout it says to use about 2 grams of ethanol. Based on the density of ethanol, it's a little over 2.5 milliliters, but I just recommend to my students to do somewhere between 2.5 and 3. The accuracy of this lab, there's going to be lots of heat losses in this lab, so it's not that important to be super accurate. So somewhere between 2.5 and 3 milliliters. All right, so that's somewhere between 2.5 and 3 milliliters, about 2.7, 2.8. Next, we're going to put our water into our little calorimeter here. And I will put our ethanol into our evaporating dish underneath. And then we are going to burn the ethanol and measure how much the temperature changes for our water and aluminum calorimeter. And then together we'll do the calculations. All right, so it looks like our initial temperature is about 19.8 degrees. And we'll ignite the ethanol. All right, so it's much easier to see now. Temperature is still rising. Now this is where you can clearly feel the heat. So if you can feel the heat, obviously there is heat loss. So like I said, this experiment is not going to be the most accurate one, but it does get the point across for how these calorimeters work and how to do calculations. Right? We're also heating up the iron ring, the clay triangle, which we are not going to be considering in our calculations. But at the end, we will find the percent difference between our value and the accepted value. And it looks like that is it. All the ethanol has been burned off. Let's turn the lights back on. Okay, that's pretty stable. About 50.5 degrees Celsius will be our final temperature. Now let's look at how we're going to do some of these calculations to figure out the molar heat of combustion for ethanol.
All right, so here's the information we got from the lab. Now this is our combustion reaction of ethanol. Now as ethanol actually combusted, it was releasing energy in the form of heat. And that heat was causing temperature of the can and the water to increase. And that we can actually calculate. So let's look at that. So we're going to write Q gained because our aluminum can and water gained energy. And it's going to be equal to MC delta T for the water. So for the H2O, we're going to figure out how much, should be a capital T, sorry, how much energy the water has increased by. And we're going to need to do the same thing for the aluminum can. So this is for the can. Okay, so we can plug in what we have. So the mass of the water, we have 97.896 grams times the specific heat capacity for water, which is 4.18 joules per gram degrees Celsius, times by our temperature change, which is final minus initial. So that's 50.5 degrees minus 19.8 degrees. And then we can do the same thing for our aluminum. So the aluminum can was 60.197 grams. And the specific heat capacity for aluminum is 0.89 joules per gram degrees Celsius. This is a long line. Times the temperature change is going to be the same. So 50.5 degrees Celsius minus 19.8 degrees Celsius. Now we can plug all of that into our calculator and we get 14,207 joules or 14.2 kilojoules. So that's how much energy the can and the water gained. And if you remember our principle of heat exchange, Q gained is going to equal to minus Q lost. So the energy has to go somewhere, right? So the energy that was lost in our reaction was gained by our calorimeter. And that is going to be equal to the number of moles of ethanol times that molar heat of fusion for combustion. So we can simply divide our answer here by the number of moles of ethanol to figure out what that molar heat of combustion is. So rearranging, we get the molar heat of combustion is going to be minus 14.2 kilojoules divided by the number of moles. Let's just calculate that on the side. If you remember from grade 11 chemistry, the number of moles of a substance is equal to its mass divided by its molar mass. So the mass of ethanol, we said, was exactly 2 grams. And the molar mass of ethanol, that's what you can get from your periodic table, is 46.07 grams per mole. So that gives us about 0.0434 moles of ethanol. So when we divide that here, 0.0434 moles, we get a molar heat of combustion of about negative 327 kilojoules per mole. And it's negative because this is going to be an exothermic reaction. Now, the actual molar heat of combustion of ethanol is negative 1367 kilojoules per mole. So again, why are these so far off? Because in our lab, obviously lots of heat is escaping. We were also heating up the clay triangle. We were heating up the iron ring. So yeah, not the most accurate lab, but it does show us how to do all the calculations. And we can figure out a percent error if we want to see a percentage for how far off we were. So we're going to take the absolute value. So find the difference between these two numbers. So 1367 minus 327 divided by that actual value, 1367, and times by 100%. This gives you a nice ratio for a percent error as 76%.